The first example that comes to mind is photons. A gas of photons. How do you generate that? A gas of photons in thermal equilibrium. Thermal photons. I have a thermal photon. You generate by making a, say, if you have any matter, you punch a hole in it, and that's a black body cavity. This matter has temperature T, and that maintains a gas of photons of temperature T inside, because the walls of the cavity emits photons and absorbs photons until it reaches equilibrium. And the photons inside, of course, has an occupation number, Nk, equal to 1 over e to the beta epsilon k minus 1. Here, mu equal to 0, that is z equal to 1, because number of photons not conserved. You recall that the chemical potential is there to express conservation of the number of particles. But for photons, the number is not conserved. So mu is 0. Why is it not conserved? Because the basic laws in quantum mechanics for the emission and absorption of photon is 1 by 1. You emit 1 photon, you absorb 1 photon. So the number of photons is not conserved. So you have this. And epsilon k is equal to h bar ck. And the state of a photon is labeled by the momentum derivative k and a certain polarization s equal to 1 or 2. Polarization, that is, the photon propagates this way, k, and the electric field either points this way or this way. Linear polarization, there are 2 degrees transverse. This is very important. There are only 2 degrees transverse to k because the photon is massless. Now, if the photon had a mass, no matter how small, then there'd be a 3rd degree of freedom, the longitudinal component. So now, there are only 2 transverse degrees of polarization. So I want to compute the number of photons H is equal to summation Nk over states, which is sum k and also s. Therefore, I get 2 summation k over Nk. And in the limit of 2v over 2 pi cubed, 4 pi integral dk k squared 0 to infinity 1 over e to the beta h bar ck minus 1. And you can easily do this integral. And the answer may be best quoted by dividing n by v. So the density of photons at temperature T is equal to 1 over pi squared integral 0 to infinity dx x squared e to the x minus 1. This is just pure number as an integral. You can do the integral on this times kt over h bar c cubed. And we call this whole thing, this is pure number kappa. And kappa is equal to 4 times the Riemann zeta function of 3, and is roughly equal to 0.23. So the number of photons, the density goes like the temperature cube. If you take a black body cavity, heat it up, the number of photons inside on average goes up like the temperature of the cube. And the internal energy is equal to 2 times epsilon k nk. Okay. Was equal to 2v over 2 pi cubed times 4 pi times n equal dk over k squared, 0 to infinity, h bar ck divided by e to the beta hck minus 1. And now you can do this, all this in call, and you get the energy per unit volume. The energy is equal to sigma times t to the 4th. And sigma is pi squared k Boltzmann to the 4th power 15 h bar c cubed. Of course, this is called Stefan's constant. So the energy density of a photon gas goes like t to the 4th power. And therefore the heat capacity goes like t cubed. Sigma, 4 sigma t cubed. So recall that CV, this goes like t cubed for photons. Whereas for Fermi gas, it goes up linearly. So again, at very low temperatures, the gas does not contribute anything to the heat capacity. An interesting way to represent this is to analyze it into frequencies. I can re-express this integral in terms of frequencies. And then I can write the frequency spectrum. Frequency spectrum. I can write uv is equal to integral 0 to infinity d omega of u of omega and t. And you can extract this u from what we have computed there, and u of omega t is equal to h bar over pi squared c cubed omega cubed e to the h bar omega over kt minus 1. And this is a Planck distribution. If you plot this u of omega t as a function of omega, then it rises like omega cubed past the maximum and goes down to 0. And this maximum is proportional to t. This is proportional to t. So that if t goes higher, you get this. This is higher t. And the total area here goes up like t to the 4th power. And it is because of this that you can, by looking at the frequency of light from an oven, you can tell the temperature. That's the principle for the pyrometry. But the most inspiring application of this is the so-called CMB, cosmic microwave background. That is, here's the sky. We look into the universe. Everywhere we look, the temperature, the whole universe is filled with a thermal photon gas, with Planck radiation, and it's uniform in all directions. With a temperature uniform to 1 part in 10 to the 5th. This color, it's a perfect Planck distribution with only, because those are one parameter to fit. You can pick any curve. You can choose the temperature to fit. And if you look at the data, it's very impressive. The points, they look like the areas are just smaller than the width of the points, all the way up to the very end. And there's a one parameter to fit. The temperature is equal to 2.7 degrees. The temperature is more precisely 2.735 plus or minus 0.05 degree Kelvin. Fit it that accurately. So that means that you look into the universe, there's a cosmic background. In all directions you look, the temperature is uniform, 2.7 degrees, to 1 part in 10 to the 5th. And if you analyze the spectrum, it falls exactly on this curve, which is somewhat awe-inspiring. And what's more, we have also measured the fluctuations from the uniformity. There are fluctuations within this 1 part in 10 to the 5th. There are fluctuations in temperature, and that fluctuation tells us a lot about the early universe. Now, this raises a question, though. This fits this formula so well. Absolutely. The only thing we adjust is the temperature. So it fits this formula perfectly. But if the photon had a small mass, even infinitesimally, we would have a factor of 3/2 out here. And this would not fit. So this is proof that the photon has exactly 0 mass. We have other evidences on the measurement of over the nature of the Coulomb field to intergalactic distances to show that the photon has a very small mass. But does this show that the photon has an exactly 0 mass? That's the question. And the answer is no. Because if the photon had a very small mass, then you have a longitudinal component. Then if the whole thing is in thermal equilibrium, you would have a factor of 3/2 here. But that component may not be coupled so strongly that it reaches equilibrium. It may not be, it may be out of equilibrium. So you cannot rule that out. And therefore, this shows that the photon probably has very small mass, but you cannot say that it's exactly 0. We you recall that when we discuss the classical gas, we talk about fluctuations in the occupation number. What about the quantum gas? We can also calculate fluctuations. In K. And this you can calculate from the grand partition function. Again, you can calculate by differentiating the grand partition function twice, like we did before. I'll just quote the formula. You can show that dnk, d epsilon k, is equal to beta minus beta times epsilon k squared minus epsilon k squared. So you can compute the fluctuation by just taking our known nk and differentiating it. And this is derived by the standard method, which I will not elaborate on. Now, when you do this, you get nk squared minus nk squared is equal to nk minus or plus nk squared, with a minus going to Fermi, with a plus going to Bose. Let's look at the two cases separately. In the Fermi case, you get nk squared minus nk squared is equal to nk minus nk squared, and these terms cancel. So you just get an nk squared is equal to nk, which is obvious. Because nk is either 0 or 1, therefore nk squared is equal to nk. So also at t equal to 0, if you look at this thing, nk squared minus nk squared is equal to 0. Because you just have so at t greater than 0, it's very small until you get to the classical case. In your case, it goes into the Boltzmann statistics, which is also small. So I will not discuss any more the Fermi case. For the Bose case, it's more interesting. For the Bose case, you get the fluctuation nk squared minus nk squared is equal to nk plus nk squared. Or if I divide both sides by nk squared, I get 1 over nk. I get 1 plus 1 over nk. And this is always greater than 100%. The fluctuation of the occupation number of thermal photons is very large. It's always greater than 100%. And this applies almost to thermal photons, photons coming out of a black body. And this means that if you take a beam, here's a black body. Contains photons. You open it up and a beam of photons come out. Thermal photons. Go along with the fluctuations are very large. The photon lump, this is called lumping of photons. That means if you go, there'll be a lot of photons and then none and a lot, they lump, they come in bunches. And this has been measured. Because if you take this beam, if you look at the correlation between time t and t plus tau, and you measure the intensity at these two spots and compare them, they should fluctuate a lot because of lumping. This is an oven. And the classic experiment is to do this. You take an oven, you take this beam, you put a mirror here, you split it. One beam goes this way, and the other beam goes this way. And you put a detector here at time t, you take it at time t plus tau, and you compare the two measurements and show that it fluctuates. And this is the classic experiment of Hanbury, Brown, and Twist. showing the bunching of photons. And this is supposed to be the first experiment in quantum optics. So, but this does not happen in a laser beam. No bunching. In a laser beam. Because a laser beam is not thermal. It's not thermal photons. It's not in equilibrium. A laser beam is a beam of coherent photons with an indefinite number of photons. A coherent state. With number of photon indefinite. With superposition of photon states. Of photon states of different n. So in a laser beam, the number of photons is indefinite. The number fluctuates, but the intensity does not fluctuate. And I think that kind of correlation measurement was the precursor to all the quantum optics experiments. So that's for the photons. So a black body cavity is a gas of photons. Now, in the similar manner, you can have phonons. These are quantized sound waves. They also obey Bose statistics. So if I have a solid, at low temperature, it's going to be a gas of phonons. That is, you don't see the atoms inside, but the only thing you see are the vibrations of atomic planes, and they generate sound waves. And those sound waves are quantized, and they are phonons. They will be positive. But here they are, the state of a phonon is K, and S is equal to 1, 2, and 3, because they are not transverse, they're longitudinal. And you can treat them in a similar way as photons. It's quite similar. So similar to photons. Except there is a cutoff frequency, omega, dBi, a dBi cutoff. Why is that? That's because you don't have a continuous medium. You have a crystal lattice. Like this. And the waves you're talking about are the oscillations of this crystal lattice. And if the crystal oscillates like this, then you have a wave. But there is a wavelength. When the wavelength is equal to the lattice spacing, then the oscillation is like this. And there's no oscillation. So beyond that point, the frequency spectrum is no longer existent. So it's a cutoff. There's a dBi cutoff. And this makes a lot of difference in the final result. This gives you the entire dBi theory of specific heat and solid state physics, which I will not go into here. But the point is that For the photon gas, the frequency goes to infinity. Here, the frequency cannot go to infinity because beyond a certain point, these oscillations are false because that's a crystal lattice. And that is the physical difference between the gas of phonons and the gas of photons. And here you have a d by temperature, d by frequency, and there's so in both cases, in the case of photons and phonons, the number of these objects are not conserved because the photons are emitted one by one, so are the phonons. They're emitted by the lattice one by one. So it is not conserved, and in that case, the chemical potential is set equal to 0, and you just have this. Now for particles, there is conservation. You have to take that into account. So that's what we're coming to. Again, I'll have to sketch the salient physical consequences of that. And the consequence of that is Bose-Einstein condensation. Or Z is e to the beta mu. And Z has to be less between 0 and 1. Z is not equal to 1, or mu is not equal to 0, because the n is conserved. Number of particles in solid is conserved. And that's because a solid is made up of ions and electrons, and the ions are made up of contain an atomic nucleus. And the ingredients of the atomic nucleus, the nucleon, is conserved. It comes from conservation of nucleons. Actually, the number of nucleons is not conserved, but what's conserved is n minus n bar. The number of nucleons minus the number of antinucleons. That's conserved by particle physics. Nucleons, antinucleons. But this is usually 0 in everyday life, so that's why n is effectively conserved. However, this is, if you apply this to a gas of electrons, then you cannot, then you have to use number of electrons minus number of positrons, because that could be created by photons. So in that case, the conserved quantity is n minus number of electrons minus number of anti-electrons. In our case, we talk about ordinary matter, so we just take the number. Say helium is n here. So let us determine Z. Lambda n cubed is equal to G 3/2 of Z. Now G 3/2 of Z is like F 3/2 of Z, except that it doesn't alternate in sign. So it's bigger than F 3/2 of Z because every term is positive. In fact, that led to the fact that the radius of convergence of that power series is 1. You cannot go beyond 1. So if I plot G 3/2 of Z, as long as I have Z, you cannot go beyond 1. It goes like this, and here it comes in a tangent and stops. Whereas f3 halves just keeps going, right? F3 goes like this. This is f3 halves. I'm sorry, f3 goes like this. This is g3 halves. And this point is 2.612. g3 halves of 1 is equal to the Riemann zeta function of 3 halves. This is 2.612. That means you have lambda cube n. Oh, that means if you want to find lambda cube n, graphically you would do this. You draw lambda cube n here. You take this and you read off the z here. Graphically. Right? So okay, I can choose any lambda 3. This is an external parameter. I can make it anything you want. Now yeah, what happens if I put it up here? What happens? There's no intersection. The curve stops here. Something is wrong. What is wrong is that when we derive this formula, the lambda cube n is equal to g3 half of z came from the derivation that n is summation nk. It came from this. And we write v over 2 pi cubed 4 pi integral ek k squared 1 over z e to the epsilon minus 1 0 to infinity. Note that by doing this, we have neglected the state k equal to 0. That one state we have neglected. So I mean, you said that one state is not that important, except when the rest of the state cannot accommodate all of it. This says that when you sum up all the occupation numbers, you have to add up to n. But you leave out that one state. N is equal to n0 plus summation k not equal to 0. Okay. And this thing gives you lambda cube n. This will give you 1 over lambda cube g3 halves of z. And we say that this can be neglected. So one state. You cannot neglect it if this doesn't hold all the particles. What do we do? We say you try to put a particle in that this only holds a maximum number of particles, not an infinite number, a maximum number. Then when the quota is reached, the particles are forced go into n0. So that when you jack up lambda, when you reach this point, you jack it up, the excited spectrum does not have room to accommodate all the particles. And the other particles are forced to go into the 0 state. That is, this curve is continued upwards. This curve really goes down here, and it goes upwards like this. So that when you take this up here, z is stuck at 1. And that's called Bose condensation. When the density and the temperature is such that lambda cube n is greater than a critical amount, a fraction of the particle must go into the 0 momentum state. That's called Bose condensation. So that is, so the solution is n is equal to n0 plus v over lambda cube G3 half. This is more correct. And this term is the Bose-Einstein condensate. And this term is less than or equal to V over lambda cube G3 halves 1. If we choose n very large so that this does not accommodate it, it has to go into this term. And that's the condensate. So we can calculate n0 over n is equal to 1 minus G3 halves of Z over lambda cube. This is equal to 0 if Z is less than 1. And it's 1 minus G3 halves of 1 over lambda cube when Z is equal to 1. So as a function of t, it looks like this. This is critical Tc. And Tc is such that 2 pi h bar squared over m ktc. Lambda 3 halves times n is equal to 1. Tc is such that G lambda cube is equal to, it's just this, 1 is equal to G 3 halves of 1 divided by the lambda critical cube. This is the condition for this transition. And then below that right here you have a finite fraction of all the particles going into one state, one single quantum state, and that's the Bose-Einstein condensate. And in the laboratory, it manifests itself as a macroscopic quantum state that has superfluidity. But I think we cannot go into all the details, but I think you can appreciate just a simple thing as the ideal Bose gas, ideal Fermi gas has so many applications. Just by looking at ideal gas, you can learn a lot, and you can use it to in many different applications in a wide range of things. So we don't have time to go to all the details, and I think that's all we can have time to talk about qualitatively. And next time we'll talk about something new. We'll talk about Brownian motion.